So students, in today's lecture, we are going to discuss a very important experiment that is known as Michelson and Morley experiment. Basically, this experiment was performed to testify the ether hypothesis. Now, first of all, let us understand that what is actually a ether hypothesis. So basically, according to the ether hypothesis, it was a general assumption of the scientific community that just like sound waves need a medium for their traveling, the light wave should also will have to use some medium for their traveling. From that point of view, this ether hypothesis was developed. So ether is a hypothetical medium which is needed for the transmission of light waves, and it was generally assumed by the scientific community that whole space is basically occupied by this ether, and this ether was a light transmitting medium which was also assumed to be a rest frame. According to this ether hypothesis, it was assumed that ether is a invisible transparent medium through which all heavenly bodies move. So in Newtonian physics, all waves are propagated through a medium, example water waves through water, sound waves through air. So from this idea of ether was taken. So now to testify this ether hypothesis, a famous experiment was performed by Michelson and Morley, the two physicists. And the experimental setup is shown in this way. So basically, in this interferometer, we are having a light source, a monochromatic light source, which is followed by a collimating lens. And then we are having a partially silvered glass plate, which is kept at point M, which is held inclined at 45 degrees to the horizontal direction. And above this partially silvered glass plate, we have placed a mirror M2 at some distance from this partially silvered glass plate M. And at the same distance, we have kept another mirror M1 in the horizontal directions. So these two mirrors M1 and M2, they are perpendicular to each other and both are having a same distance from this partially silvered glass plate. And below this glass plate, we are having a telescope T. So basically this Michelson interferometer is an optical device which is utilized for producing the phenomena of sustained interference. But here we are using this apparatus for entirely different purpose. Here we are using this apparatus for testifying the ether's existence. So briefly, I had described the different components of this experiment. So this is the simplified ray diagram of this Michelson interferometer. Now let me elaborate this interferometer by this experiment, this figure. So this is our light source from where light is moving, and this is our collimating lens. So basically in this figure, we are explaining the relative separation of this mirror with respect to ether frame. So ether is a stationary frame, and we have shown the relative separations of the mirror, these two mirrors M1 and M2 with respect to ether frame, and we have calculated the time with respect to both frames, earth as well as ether. In the horizontal direction, we have calculated the time taken by the light beam, which is traveling from this partially silvered glass plate towards this mirror in horizontal direction, and then the time taken by the beam in returning towards again this mirror, this partially silvered glass plate. And in the vertical direction also, the same time we have to calculate. But these two times you have calculated with respect to the different frames. For example, the time in the horizontal direction has been calculated with respect to earth frame, and time in the vertical direction has been calculated with respect to ether frame. So now let me explain that how these two times has been estimated. First of all, let's talk about the time in the horizontal direction. We know that the velocity of light v, that is the velocity of light with respect to ether frame, is c in all directions. So this is the velocity of light, that is c in all horizontal, vertical, in all direction. And velocity of earth, capital E for earth, with respect to ether is v in left to right direction. In left to right direction, that is assumed to be positive. So we have to estimate here the velocity of light. Thank you. So basically we have to first of all calculate the velocity of light with respect to earth, because we are performing the experiment from the earth. The velocity of light with respect to earth. So that will be given by this formula. Velocity of light with respect to earth is equal to velocity of light with respect to ether plus velocity of ether with respect to earth. Or this can be written as velocity of light with respect to ether minus velocity of earth with respect to ether. So both velocity we have assumed positive in left or right direction. So the velocity of light with respect to ether will be c minus v when light beam is approaching from the partially silvered glass plate towards the horizontal mirror, from this glass plate towards this mirror M1, and this mirror is M2. Both are having the same separation for this from this glass plate. So velocity of light with respect to earth, now we have calculated, that is equal to c minus v. So time of approach from this partially silvered glass plate M towards the M1 will be t is equal to L divided by c minus v. When light beam will return from the mirror M1 towards the glass plate, the time will be L. So this will become minus. So minus c minus v, that is minus c plus v, and minus sign will be neglected because it is just indicating the direction. So it will be c plus v. So this time t1 we have estimated. This time t1 we have estimated with respect to earth frame. Now for estimating the time t2, Now, for estimating the times which is taken by the light beam in moving towards this upper mirror. So this time basically we have calculated with respect to ether frame, not with respect to Earth. Though we are performing the experiment with respect to Earth, for the sake of convenience, we are estimating this time with respect to ether frame, which is assumed to be a rest frame. Now, all of us know, according to the Galilean transformation, the time is an invariant quantity. Whether we measure this time from the Earth frame or from the moving frame, it is not going to make any difference. So that's why we are estimating the time towards this upward mirror with respect to ether frame. Now what we are observing? We are observing, so initially the light beam was moving from this partially sideward glass plate towards the upward mirror. The distance between this glass plate and the mirror is L. Now what happens? When light beam moved towards this mirror M1, let's say it takes a time t. In the same time t, our Earth will move in left to right direction with velocity v. So our mirror will shift from this initial position toward this position. So this is the observer. This has been observed by the observer who is standing, who is sitting in the stationary frame ether, and he is looking into this Earth frame. So he is observing that Earth has been moved from left to right. So this whole apparatus of Michelson and Morley will also move in left to right direction. So light beam will basically not reach toward this point. It is going to reach towards this point. And let's say t is the time taken by the light beam in reaching from this point to t. Now our glass plate is situated somewhere here in this middle. So now light beam will approach from this point towards this point, but in the meantime, the light will reach from this point to this point. This plate will shift from this point to this point. So finally, the light beam after reflection from this upward mirror is going to meet the mirror at this point. This is the final point where this light beam is going to meet this mirror. Now, so we have to estimate the whole time in this journey. Let's say this t, the time taken by the light beam with respect to ether frame from this point to this point is t. So the distance covered by the light beam will be ct. So in this way, we can say that mirror has been shifted. Okay. So this is the time. So this distance is ct. This distance is L. This is ct and this distance is L. And this is Vt. So in the time t, the light beam reach from this point towards this point. In the same time, our apparatus will move with velocity v, which is the velocity of Earth with respect to ether, that is t, Vt. So from this right angle triangle, we can easily estimate this distance is L, that is Ct square is equal to Vt square plus L square. Or we can write T square, that is C square minus V square is equal to L square. Or T is equal to L divided by square root of C square minus V square. So total time will be, T2 will be twice of this, that is 2L divided by square root of C square minus V square. So this was T1 and this is T2. So T1 was the time taken by the light beam in reaching towards mirror M1 and then coming back. And T2 is the time taken by the light beam in reaching towards the mirror M2 and then coming back. So these two times has been basically estimated in two different frames. So the time for the horizontal mirror has been calculated with respect to Earth frame, and time for this vertical mirror has been calculated with respect to ether frame. Now, you can ask a question that we are performing the experiment from the Earth, then why this time has been estimated from the ether frame? As I told you earlier, that ether is basically a rest frame. And according to Galilean transformation, time is an invariant quantity. Whether we measure it from a rest frame or from a moving frame, it is not going to make any difference. So that's why, just for the sake of convenience, we have calculated this time t2 with respect to ether frame. The same time can be estimated directly also with respect to Earth frame. So I will show in the coming slide that thing. Now, let's suppose that we are interested in calculating this time directly with respect to Earth frame. We don't want to go towards the ether frame. Then how we are going to do this? Now, suppose we are interested in calculating this time for this vertical mirror M1 directly with respect to Earth frame by not utilizing the ether frame concept. So by using the concept of the reverse swimmer problem, we can easily estimate the time. Suppose all of us know about this famous reverse swimmer problem. Suppose a river is flowing, velocity of river with respect to ground is, let's say, v in left or right direction. And any swimmer who swims with the velocity of swimmer with respect to river is, let's say, is equal to v dash. If he wants to cross this river, then he will have to move in this direction, in leftward inclined direction. Then only by the relative velocity concept, we can understand that he will directly cross this river and will reach a opposite end. So velocity of swimmer with respect to river should be leftward inclined. Then he will directly cross the river and will reach at this point. So by using the same concept here, let's say that the velocity of light with respect to ether, that is equal to c, that should be in this direction. Then only we will observe from the Earth that velocity of light with respect to Earth will be in vertically directly upward direction. In this way, it will be in vertically upward direction. That is velocity of light with respect to Earth, and let's say that is equal to some x quantity. And as I told you earlier, that velocity of Earth with respect to ether is v. And by the formula we've discussed in the earlier slide, that velocity of light with respect to Earth is equal to velocity of light with respect to ether minus velocity of Earth with respect to ether. So velocity of Earth with respect to ether is in positive direction from left to right. So in right to left direction, its value will be minus v. So in this way, minus value of velocity of earth with respect to ether will be from right to left. So this is equal to v. So from this right angle triangle or the triangle rule of vector addition, we can easily estimate the value of x. The value of x will be c square is equal to v square plus x square, or x square is equal to c square minus v square, or value of x will be equal to square root of c square minus v square. So this is the velocity of light with respect to earth. So make sure that c is not here the velocity of light with respect to earth. C is assumed here the velocity of light with respect to ether. So now by taking the summation of these two times, this is T1 is the time for the horizontal mirror M1, which we have already estimated with respect to earth frame. So by doing the simple calculation and using the binomial expansion, we can find the value of T1. The value of T1 comes out to be 2L divided by C, 2L divided by C within bracket 1 plus V square by C square. And time taken for the light to travel towards the mirror M2, which we have estimated in both frames, earth frame as well as ether frames. So its value comes out to be T2 is equal to 2L divided by C, 1 plus V square by 2C square. Again by using the binomial expansion. By taking the differences of these two times, we can calculate the time difference between the two beams. The beam which is moving towards the horizontal mirror and the beam which was traveling towards the upward mirror. So the time difference value comes out to be LV square upon C cube. Now since we are performing from the experiment with respect to earth frame, so with respect to earth, due to this time difference which we have estimated LV square upon C cube, we can calculate the value of the fringe separation, and its value will be LV square upon C cube multiplied by C. Now here the C is the approximate velocity with respect to earth frame. C was actually the velocity with respect to ether frame. In case of earth, its value was not assumed to be C. Its value was either C minus V or C plus V or square root of C square minus V square. But here we are just neglecting the value V and taking its approximate value just equal to C. So the path difference or the distance covered by the light beam in this time delay will be LV square multiplied by LV square upon C cube multiplied by C. So that will comes out to be LV square upon C square. So we can calculate the fringe shift. The fringe shift should be LV square upon C square lambda. By all of us know that the path difference is equal to n lambda. So path difference is here equal to LV square upon C square. LV square upon C square. After multiplying this LV square by upon C cube by C, we will get LV square upon C cube. So this should be equal to n lambda, and the value of n will be equal to LV square upon C square lambda. Since we are performing we are performing this experiment with respect to Earth frame, and our Earth is moving from left to right direction. So our whole apparatus is moving from left to right direction. So this fringe will also move in left to right direction, and we won't be able to measure any fringe shift as such. So for measuring this fringe shift, what we're going to do, we have to basically rotate this whole apparatus through a 90-degree. So what will happen after rotating this apparatus through a 90-degree? That our fringe will shift in just opposite direction. If it was earlier in rightward direction, now it will shift in leftward direction. So we can say that here that basically if our fringe was in this position, so related to the origin in this position, this is the fringe shift position, that is LV square upon C square lambda. Now if we are going to rotate the whole apparatus through 90-degree, so our fringe will shift in just opposite direction in this way, and its value will be minus LV square upon C square lambda. So exact value of the fringe shift will be LV square upon C square lambda minus LV square upon C square lambda. So this should be equal to 2 LV square upon C square lambda. So this is the total value or the exact value of fringe shift which should be observed by the observer who is standing on the Earth. So basically our observer is performing this whole experiment with respect to Earth frame. But conventionally in this literature and the books, the time has been shown to be calculated with respect to both frame, Earth and ether frame. So that's why that complicated figure has been drawn in which the relative separation of mirrors has been shown. But it is not necessary that we estimate both these time with respect to one with respect to Earth and with respect to ether. We can directly estimate both time with respect to Earth frame also. That's my point. So the value of fringe shift is here estimated to be 2 LV square upon C square lambda, which has been estimated after rotating this whole apparatus through a 90-degree. Now by substituting the standard values of L, V, C and lambda, we can estimate the numerical value of the fringe shift. So after substituting the standard values of length is the arm of the interferometer, which is the separation between the partially silvered glass plate and the mirror, and then substituting the value of V, that is the velocity of light, that is the velocity of Earth with respect to ether frame, and C is the velocity of light with respect to ether frame, and lambda is the wavelength of monochromatic light source. The numerical value of this fringe shifts comes out to be 0.4. So our theory is telling that this value should be around 0.4. But what was actually observed by Michelson and Morley after performing this experimentally, that fringe shift comes out to be 0.01 only. So there is a huge difference. Theory is telling us that fringe shift should be 0.4. And what we are observing, we are here observing the value of fringe shift only 0.01. And that 0.01 is also within the limits of experimental error. So finally, it was declared by Michelson and Morley that result of this experiment is null and void. And actually the fringe shift what we are observing here experimentally 0.01 is basically due to some experimental errors. And actually we are not observing any kind of fringe shift here. So the result of this experiment was declared to be null and void. That means if we are not getting any fringe shift, that means ether does not exist at all. When ether does not exist at all, so the idea of the scientific community that just like sound waves, light wave also needed a medium for their traveling purpose was finally discarded, and it was concluded that light beam doesn't need any kind of medium for their travel. They can travel through a free space. and the velocity of light, that is always constant, that does not depend upon the relative motion of source and observer. So this is the famous conclusion which was drawn on the basis of this experiment by Albert Einstein. So all of us know that Albert Einstein gave the two postulates of the special theory of relativity. The first postulate was that laws of physics remain same in all inertial frame of references, and second postulate was that velocity of light is always constant. It doesn't depend upon the relative motion of source and observer. So this principle of constancy of the velocity of light was observed on the basis of this Michelson Morley experiment. So as I told you that result of this experiment was declared null and void but scientific community was not at that time was not convinced directly by this negative result. The scientific community of that time, they tried to give certain justifications in favor of these negative results, and they tried their best to save this ether hypothesis. The first explanation which was given to save this ether hypothesis was the ether drag theory. According to this ether drag theory, the scientific community mooted the idea when any kind of heavenly body moves with respect to ether, it will drag ether along with its motion. Then what will happen? If any body is going to drag ether with that, then the relative velocity of that body with respect to rest frame ether will become 0. And in that case, there will be no time differences for the mirror in M1, M1 and M2. When there will be no time difference, there will be no path difference and there will be no fringe shift observed. So this was the one idea which was given in favor of this ether hypothesis. The other one was the length contraction. According to this concept, there will be a contraction in the length along the direction of motion, which is given by L multiplied by square root of 1 minus V square by C square. As in the experiment, we have seen that our earth is moving from left to right direction and our interferometer is also moving from left to right direction. So in the horizontal direction, the arm of the interferometer, which is having a length L, that will be contracted by the formula L multiplied by square root of 1 minus V square by C square. Now what will happen by this? By using this length contraction, the time for the two mirrors M1 and M2, they will become exactly, or they will become approximately equal to each other. So T2 minus T1, that is a time difference, that will become equal to 0. So these were some ideas which were given by the scientific community in favor of ether hypothesis. But very soon all these ideas were discarded by the scientific community. First of all, this ether drag theory. Basically, this ether drag theory was entirely a theoretical idea and it was not having any experimental support. So that's why this idea was not accepted by the scientific community. Similarly, this length contraction hypothesis was also a mathematical conjecture. It was also not having any experimental basis for this experimental basis for this kind of length contraction formula. So finally, the scientific community concluded that ether does not exist at all and light waves does not need any kind of medium for their travel, and velocity of light is always constant and it is not going to depend upon the relative motion of source and observer. So for finally and for all, it was concluded that the result of the Michelson and Morley are null and void and ether does not exist at all. So now the conclusion which were drawn on the basis of null and void result, again I am repeating that velocity of light is always constant. It is not going to depend upon the relative motion of source and observer. So that's all for today's lecture. Thank you to all of you.